Okay, let's do some review. I'm not going to do all of the problems on the review. You already have the answers. I'm just going to pick, I don't know, maybe half of them for us to do together. Okay, this first one. Identify each graph below as exponential, linear, logarithmic, or quadratic. First one is a line. Which one would be quadratic? Remember, quadratic is like x squared. It's a parabola. This one here is a parabola, so it would be quadratic. These two are either exponential or logarithmic. You need to recognize what the graph of each looks like. An exponential function has a horizontal asymptote, which this one has. And the second or last graph has a vertical asymptote. This one is exponential, and this last one is logarithmic. Logarithmic functions they start here, and if they're not transformed or shifted, they look like this. Where exponential functions have a horizontal asymptote along the x-axis and cross the y-axis at 1. They are inverses of each other. So if you see it going up with a horizontal axis, or even coming down this way, this is when the base is less than 1. Then you know it's exponential. And if it has a vertical asymptote, you know it's logarithmic. Okay, let's do this system of linear equations, problem 2. (5x plus 9y minus 5z equals 86). X plus 2y minus z equals 18. And 6x plus 8y minus 5z equals 90. Now remember the way we solve a system of linear equations with 3 variables is we want to pick either x, y, or z to eliminate from 2 different pairs of equations. We can choose to eliminate x. I'd need to multiply the second equation by a -5 and a -6 to cancel out with the 6x and the 5x. Or I can eliminate the z's. I would multiply the second equation by a -5. So a positive 5z and a negative 5z would cancel. I'm going to do x. It doesn't matter which one you do. So I'll take the first equation and the second equation to eliminate x, and then I'll take the second and the third equations to eliminate x. I'm going to do -5 times the second equation, which I'm going to call line 2. It's a line in 3 dimensions. And I'm going to add to it line 1. This is the way I like to write it. So -5 times the second equation is -5x minus 10y plus 5z equals, what's 5 times 18? 50 plus 40, -90. And then we check that we didn't make any mistakes. -5, -10, +5, -90. And we add to it the first equation, or line 1. And then we add each term. The 5x's cancel. -10y, 9y is -y. These z's cancel as well. -90 plus 86 is a -4. -y equals -4. That's usually an equation, not just an answer for y. In this case, we get y is equal to 4, which is nice, but it doesn't usually happen that way. So I'm going to continue as if we didn't already solve for y. Now I'm going to pair the second and the third equations. I'm going to multiply the second equation by a -6. So -6 line 2 plus line 3. -6 times an x, -6 times a 2y, and -6 times a -z. And -6 times 18 is a 60 and a 48, or -108. Let's double check that. -6, -12, +6, -108. 60 and 48. Excuse me. Then we add to it the third equation. Don't go to sleep, computer. The x's cancel. Negative 12 and 8 is negative 4y. 6 and negative 5 is a plus z equals negative 18. So I now have a smaller system with two equations. My first equation is y equals 4, and my second equation is negative 4y plus z equals negative 18. Our next task, whoops, sorry about that, guys. Keep an eye on the screen. Our next task is to solve this smaller equation. In this example, y is already solved. So how do you finish solving? Plug y into the second equation so you can evaluate for z. If that isn't solved for one of the variables, which usually it won't be, then you would use substitution or elimination to solve. I'm going to go ahead and substitute this y in, so I get negative 4 times 4 for y plus z equals negative 18. And simplify. Add the 16 to the other side, and I get z equals negative 2. So I have y, I have z. To find x, I plug both this y and this z back into one of the original equations up here. Let's use the second one. So x plus my y, 2 times my y value of 4, minus my z value of negative 2 equals 18. Simplifying, we get x plus 8 plus 2 equals 18. Combining the 8 and the 2, subtracting the 10, get 8. Once you have your answer, I have x, y, and z is down here. We want to check it. So we're going to plug 8 in for x, 4 in for y, and negative 2 in for z. And I'm going to do this in my head real quick. Here we get 40 plus 36 is 76, plus 10 is 86. You can check them all. I'm going to do 2 of them. 8 plus 8 is 16, minus negative 2 is plus 2, 16 plus 2 is 18. 2 of them worked, I'm assuming all 3 work. Now, how do we present our answer for a system? We want to write it as an ordered pair or triple, in this case, or a point. There's 3 variables, so we'll write it as a triple. X is 8, y is 4, and z is negative 2. So this is my answer to the system. Okay, the next one. Looking at this polynomial, we need to decide if it has a positive or negative leading coefficient, and assuming there's no other turning points off of the viewing window, so nothing happening on the left, right, or the bottom or the top that you can't see, all of the turning points are here. Does the polynomial have an even or an odd degree? Pretty much, which of these 4 cases is it in? Squared would be even, cubed would be odd. Since both sides go down, we know that it's going to be odd. So it's not either of the positive cases. Our negative options are down on both sides, or up on the left and down on the right. These are both negative. And then the positive cases would be up on both sides, or, oops, you can't see that. Up on both sides, or down on the left and up on the right. Okay. Or we can even just look at these 4 cases right here, might be easier. Even positive leading coefficient goes up on both sides. Just think about what positive x squared looks like and what negative x squared looks like. That's how I remember these. Positive x squared looks like that, negative x squared looks like this. Positive x cubed looks like this, negative x cubed looks like this. So since my picture has both sides going down, I know that I have to be in this situation, which is a negative leading coefficient and an even degree. You can also count the number of turning points. An odd number of turning points means an even degree. An even number of turning points means an odd degree. That's another way you can remember it. Okay, moving on. Let's do number 5. We're just going to do part of 5, not the whole thing. If f is equal to 2x minus 3, and g is equal to x to the 4th minus 3x plus 2, what is f minus g? F minus g, you just take each of the equations. I would put them in parentheses so you don't forget to distribute this negative sign, minus the second equation g, x to the fourth minus 3x plus 2. Then you'd want to distribute this negative, so it becomes a negative x to the fourth, a positive 3x, and a negative 2. Then we combine like terms. I only have one x to the fourth term, so it's a negative x to the fourth first, no cube, no square. Then we combine our x's. 2x plus 3x is 5x. Combining our negative 3 plus a negative 2 is minus 5. So that would be f minus g. F times g, I skipped f plus g because it's similar to this first one, but easier. F times g, we want to use parentheses so we don't forget to distribute multiplication. You can also use the box method if you prefer. The box method would be to write it like this. And we do 2x minus 3 times x to the fourth minus 3x plus 2. And then you multiply each of the parts and you put your answers in your box, and then you combine like terms. I'm going to do it this way though. 2x times x to the fourth gives me 2x to the fifth. 2x times negative 3x gives me negative 6x squared. 2x times 2, positive 4x. Then negative 3 times x to the fourth is a negative 3x to the fourth. No like terms, so I'm writing it in the middle. Negative 3 times negative 3x is a plus 9x. And then negative 3 and a 2 is a minus 6. Add the two together. I get my 2x to the fifth, my negative 3x to the fourth, my negative 6x squared. Add those two, we get plus 13x and a minus 6. That would be f times g. I don't have anyone here correct me when I make mistakes, which happens once in a while, so let me just double check I didn't make any. 2, negative 3, negative 6, 13, and negative 6. Good. And this one, it looks good too. All right. Number 6. If f, similar to the previous one, but not quite the same, is equal to 2x squared minus 3, and g of x is equal to 5 minus x, find f composed with g. That's what that little circle means. It means I'm doing composition of functions, which you can also write like this. F parentheses f of g of x. So the way you solve this is you start by writing the g function inside the parentheses, 5 minus x. Okay. Now we want to write our f function. That's the outside function. So whatever I see for f, I'm going to write that here, except instead of writing x, when I get to an x, I'm just going to write a set of parentheses. So 2 times my parentheses squared minus 3. That's my outside f function. My inside function goes inside the parentheses, which is the g, the 5 minus x. And then you have to simplify. Remember, 5 minus x is not 5 squared minus x squared. We're foiling, we're distributing like we just did in the previous example. And you can do that with the box method, or you can do it by using FOIL. First terms, outside terms, inside terms, last terms. 5 times 5, 5 times negative x times 5, negative x times negative x. Combine like terms, and we get our quadratic. That goes in place of the 5 minus x squared in parentheses. I'm going to put it in descending order of degrees of powers. And then we have to distribute the 2. And combine like terms. If you need to push pause at any point to catch up, that's fine. Recordings are nice for that reason. Also, if I go really fast, you can choose to have it go slower. I want to get through more information though. Okay, that's the answer. So we're done with that problem. That's a composite function, that's f composed with g. Now we're going to skip 7, 8, and 9. I don't have time to do all of them. we're going to do 10. Determine the linear function in slope-intercept form. That's y equals mx plus b. Today, when we get to a formula that you should know, I'll try to remember to box it so you can make a list of formulas. You can't take them, cannot use a list of formulas for the final exam, but you should memorize them. And that's the only formula we have so far. Determine the linear function. Now, whenever you see in a problem the linear function, that means you actually want f of x equals mx plus b, not y. So this is how our answer should look, f of x equals, whose graph is perpendicular to the graph of g, where g of x is equal to 2x minus 7. If we want perpendicular, that means we look at the slope of this function right here, 2, perpendicular. And we need to take, this means the slope would be the negative reciprocal. Negative 1 over 2. If it's a fraction, like 2/3, then it becomes negative 3/2. If it's 1 over 3 or negative 1 over 3, it would become positive 3 over 1. If it's positive 3, then it becomes negative 1 over 3. That's how you do negative reciprocals. Change the sign and flip the fraction. So since g had a slope of 2, the slope I want is going to be negative 1/2, 1 over 2. Let's keep reading. And it passes through the point 0, 3. Now, if the point happens to be on the y-axis, then it's your y-intercept, which is this case. It won't always be the y-intercept. If it's some other point, then you'd want to plug that point in for x and y, and then use that to find b. But here, this is actually our b, because it's a y-intercept. So we know b, we know the slope, we can use those to find our function. F of x equals negative 1/2 x plus 3. I know this is pretty basic, but I want to make sure we all know how to do that. There's a lot of problems with lines, finding equations of lines here on this review. Let's do 12 next. Determine the inverse of f of x equals 5 to the x. Remember, the process to find inverse functions is you start by writing y equals instead of f, and then switch your variables, and then solve. This one doesn't have a lot of solving to do. If you don't show any work, it's understandable. The inverse of an exponential function is a logarithmic function with the same base. So if you remember that, you can just write the answer down here. But if you don't, then go ahead and do this process, which is write y instead of f, change your variables, and then you want to get y by itself, which is this exponent. The way we define logarithms is the log right here is equal to the exponent. So that y is the exponent of when I have base 5. Another way you can think about this is I want to change the form. The way we change forms is we always start with the base, whether it's a log or an exponent, and then we do an arrow to the other side, going all the way around. So this would be log. Since it's exponent now, we want to change it to log. We're changing from exponential form to logarithmic form. Log base 5 of x equals y. We solved for y, and then we write it as an inverse function. F inverse of x equals this equation, log base 5 of x. So whether you go through this process or you just remember that those are inverses of each other, either is fine. All right, let's do 14. Determine the points of intersection of f and g when f is equal to 2 to the x plus 1 and g is equal to 4 to the 2x minus 3. So this is an important concept we're going to talk about right now. Remember how I said when a problem asks for a linear function, you need to remember to write f of x and not just y equals. You're going to get a lot of problems on the test when they're asking for points as your answer, and a lot of problems when they're asking to solve equations. So let's write this at the top of this page. This is one thing that's important that I want you to know, is when a problem asks to solve an equation, your answer should be in the form of x equals some number or multiple numbers. Or it could be y or z, whatever the variable is you're solving for, but it's just one variable equals an answer. On the other hand, if it says find a point, whether it's an intersection point, so points might be intersection points or x or y intercepts. Those are points on graphs. Intersection points, x intercepts, or y intercepts. If you're finding a point, then you need to write your answer in the form of x comma y point versus solving an equation, which is just an x value. So my suggestion is, when you're doing the test, find your answer and then reread the problem and ask yourself, are they asking me for a point or are they asking me to solve an equation? Because they are very tricky and they do both in similar types of problems. This problem, 14, let's read it together, says, determine the point or points of intersection. So our answer should be in the form of x comma y, points of intersection, don't forget that. Of f and g when this is f and this is g. So here's f and here's g, we want to find the point of intersection. You can find that looking on a graph, but we don't have the graph. You don't have to graph these either. The way you solve these is you set the two functions equal to each other, and you solve the equation. But when I solve an equation, I'm just going to find an x value, but I want the point. So first you find the x value, and then you take that x and plug it back into either f or g to find y. And it doesn't matter which one you plug it back into, because this is a point where both graphs cross. So they should give you the same y value. All right, exponential equation, this is good practice. If I can get both sides to have the same base, it's a lot easier to solve. And I can, because 4 can be written as 2 squared, which matches this base 2. So I'm going to write 4 as 2 squared, leave everything else the same. And now I need to know rules of exponents. This 2 raised to this 2x minus 3 means I multiply those together, the exponents. So 2 times 2x minus 3 is equal to 4x minus 6 as the new exponent. Now I have the same base, and I can just set the exponents equal to each other. This is called the, I think our textbook calls it a property of equality. I usually call it a one-to-one property. Now we want to combine our x's and the constants on the opposite side. So we'll subtract this x. I'm going to add this 6 to the other side. So I get 4x minus x, 3x equals 1 plus 6, 7. Divide both sides by 3. That's my x value, 7/3. It's a fraction, hopefully it's right. I have the answers so I can actually check them. It is. Now we need to find y. So we find that by plugging this back into either f or g. F looks a little bit easier to plug back into. F of 7/3 is equal to 2 to the 7/3 plus 1. That would be 7/3 plus 1, get a common denominator. That's 2 to the 10/3. And you can actually leave your answer just like that. That's the y value of your point. You could rewrite that with a cube root, but we haven't really practiced that in this class, so I would just leave it like that. So the point where these two graphs intersect would be x 7/3, comma y 2 to the 10/3. That's the point where they intersect. Okay, next. 15. Let's look at these graphs. The graphs of f and g are both graphed on the coordinate system below. 3 different examples. The reason I'm giving this one right after the one we just did is to see the difference between the wording of the two equations. The previous one, we didn't see the graphs, but we wanted to find where they intersected. Here we see where they intersect, but the problem isn't actually asking for the points of intersection. It says find the solutions to the equation f equals g. This is f, and this is, it doesn't really matter which is which. We can just pick one. This might be f, and that's g. This is f, and this is g. These are 3 different problems. Where do they intersect? Right here, right here, right here, and right here. Those would be the points of intersection, but since this problem is finding a solution to an equation, the way you write your answer to a solution of an equation is always x equals a number, not a point. So you just look at your points of intersection and you find their x-coordinates. So for this first one, the answer would be x equals 4. The second would be x equals -1 or 2. This third would be x equals 0. Hopefully that makes sense. All right, 17. Find the domain and range of a parabola or a quadratic equation. I was going to do a previous problem that practiced finding the vertex of a quadratic, but we're going to have to do this here anyway, so we'll practice that here. Put your answer in interval notation for domain and range. All right, parabolas can either look like this or like this. What is the domain for any parabola? It's always -infinity to infinity. But these two different situations have different ranges. If the vertex is h comma k, could be any numbers. K is the y-intercept, h is the x-intercept. Our range for this first example would be starting at k going up to infinity. So it looks like this. A bracket at k, because there's a filled-in point there, all the way up to infinity. For the second case, it starts at -infinity all the way down as far as you can go, and it stops at the y value of k. So we write that as -infinity to k bracket. So our answer is going to look like one of these two. The domain we already know is -infinity to infinity for parabolas. So let's go ahead and write the domain at, actually we're going to write that last. But in order to find the range, we need to know the vertex. So let's practice finding the vertex. If the problem is given if the equation is given in vertex form, which, you know, we can look at it real fast because there was another example in vertex form right here. This is problem 7. The vertex is always opposite sign, same sign. So -3, -4. But if it's multiplied out, you either need to get it into vertex form, which involves completing the square, or you can use the formula, which you may as well use the formula for h since they didn't tell you not to. -b over 2a. This is a formula you should memorize. So let's add this to our formula list today. In this situation, we have a is 1, b is -8, and c is 2. So -b would be a -8, or a +8, over 2 times a, which is 1. So we have +8 over 2, which is 4. That's h, but I want to know k in this situation because that's going to help me find my range. The way you find k, or the y coordinate of your vertex, is you just plug your h value, 4, back into your function. 4 squared minus 8 times 4 plus 2. This is equal to 16 minus 32 plus 2, which is 18, minus 32, which is -14. That's my k, and that's my h. So let's state the domain and the range now. The domain is -infinity to infinity. It might not be a bad idea to do a quick sketch of your parabola. All you need to do is look at if it's positive x squared or negative x squared. Positive x squared looks like this. So my range is going to be in the form of k up all the way to infinity. And my k is a -14. And that's the range. And we had to find the vertex to find that range. Okay, next. Number 19. If the parent function f of x equals log of x is shifted right 2 units, arrow represents the words shift right 2, and then reflect over the x-axis, reflect over x, what will be the resulting function? Okay, a left-right shift shows up right next to the x. So that would be a log of parentheses. If it's +2, you're shifting left. If it's -2, you're shifting right. We want right, so we'll put -2. It's always the opposite sign when it's next to the x. For up-down shifts, you don't have to change the sign. So up is plus, down is minus, and you would put that out here. A reflection shows up as a negative sign in front. That's reflecting over the x-axis. If you're reflecting over y, you need to put the negative right next to your x. But they wouldn't have done that here because it makes the problem more complicated. This is our transformed function, so we'll call it something different, g. And let's just make sure we did it right. This tells us to shift right to and reflect over the x-axis. Rereading the problem, it says, starting with the log of x, shift it right to, reflect over x. What will the resulting function be? So the problem is asking, find the function. There it is. We answered the way they asked it. Okay, this next one, 20, we're going to just do it here on this paper. If you need to push pause to write those numbers down or print out this review and just write on the paper, it's up to you. We want to decide if these set of ordered pairs represent inverse functions. No, let's read it again. Give the inverse function of the set of ordered pairs, or give the reason the inverse function does not exist. So when does an inverse function exist? It has to be a one-to-one function. So the way you do this is first you have to check if it's a function, and then second, if it's a function, you check if it's one-to-one. So how do we know if a function is, how do we know if a relation is a function? Looking at some examples of graphs up here. If it passes the vertical line test, you know if it's a function. So this is all of these are functions actually, because they all pass the vertical line test. It has to pass the horizontal line test to be one-to-one. This horizontal line passes through twice, so it is not one-to-one. Parabolas are not one-to-one functions. On the other hand, lines are one-to-one. This horizontal line only crosses this single line once. But how do you think about that in terms of points? So with graphs, it's easy with the vertical and horizontal line tests. But what are we looking for here? If it doesn't pass the vertical line test, it means you have 2 points on top of each other. So for instance, if you have a sideways parabola, that would not be a function because it has a point on top of 2 points on top of each other. What is the same? Here, the x's are the same. So this might be 1, 1 and 1, 3. Their x's match. On the other hand, to not be one-to-one, the x's are different. Let's pick ones that are easier to find. These right here, for instance. This is -2, 0, and 2, 0. The x's are different, but the y's are the same. So to look for one-to-one, we look for matching y's. To look for whether or not it's a function, we look for matching x's. So let's do that here. This first example. First, we're going to check if it's a function. Is it a function? If it is it one-to-one? If it's not a function, it can't be one-to-one because we only talk about one-to-one functions, not one-to-one relations. If it's both of them, then we know the inverse exists. And the way you find an inverse is you just switch the coordinates. But we won't do that unless it satisfies both of the tests. So first we'll look at x coordinates. 2, 4, 9, 7, 5. Do any of them repeat? No. That means it's a function. If they did repeat, then you'd want to make sure their y's were different, that they actually represented 2 different y's. Because if you just list the same coordinate 1, 1 twice, it doesn't mean it's not a function. That's okay. All right, so this one is a function. Let's see if it's one-to-one. Now we're going to look at the y values, the y coordinates. Let me use a green pen. 1, 2, 3, 6, and 4. They're all different. That means this one is also one-to-one. If it's a function and it's one-to-one, then you can find its inverse. So this inverse would be 1, 2, just switch the coordinates. 2, 4, 3, 9, 6, 7, and 4, 5. All right, let's check the next one. Let's see if any x's repeat. 2, 4, 9, 7, 2. Okay, our 2's repeated. It still could be a function though. Just because they repeat doesn't mean it's not a function. We need to check their y's. 1 and 4 are different, which means this represents 2 different points on top of each other. That is not a function. Not a function. If it's not a function, we don't care if it's one-to-one. So the problem says, find the inverse function if it exists, or give the reason the inverse function does not exist. So for this one, the inverse function does not exist, and you'd say the inverse function doesn't exist because f is not the relation, because the given set was not a function to start with. Does not exist because the set is not a function. they told us that these are sets of ordered pairs. So if you forget that word set, just look at the way it's given. This is a function of the set of ordered pairs. The set is not a function. Okay, last one. 2, 4, 9, 7, 5. Those are all different, so it is a function. Now we need to see if this one is 1 to 1. So let's check the y coordinates. 1, 2, 3, 6, 2. We repeated 2 twice. Let's make sure the x's are different. 4, 2, and 5, 2. That represents 2 points that are side by side. That means this one is not 1 to 1. So for this one, you'd say the inverse function does not exist because the set is not a 1 to 1 function. Or the given, it is a function, but it's not 1 to 1, something like that. So ... the set is a function, but is not 1 to 1. Is not 1 to 1. All right, let's move on to these. How are we doing for time? I may not get through everything I wanted to today. We'll see. 22. Find the x-intercepts if they exist for this function. And then the next one is determine the zeros. I wanted to do these one right after the other to remember what I said earlier. Think about if the problem is asking you for a point or an x value. X-intercepts are points. So here you're looking for 1 or more points. Where zeros are not points. Zeros are x values. Okay, so this is a very similar problem. The process is identical to finding these points or these zeros, but your answers are different. They both have the same x, but in terms of a point, you also have to put comma 0 for x-intercepts. Let's do 22 first. So given f of x equals 5 times x plus 4 squared minus 15. The question says find the x-intercepts. For both of these types of problems, to find x-intercepts or zeros, you want to set the equation equal to 0. For x-intercepts, you set y equal to 0 and solve for x. For y-intercepts, you set x equal to 0 and solve for y. Remember, our y is our function. F is the y value. So we put 0 in for f. And that's also the same thing you do to find zeros, which is the next problem, 23. All right. 2 ways to solve this. We can multiply it all out and refactor, or a little bit more straightforward way is to try to get the x plus 4 by itself. And then we can square root both sides. I'm going to do it that way. So add 15 to the other side. We are undoing an equation. When you are solving equations, you do order of operations is PEMDAS backwards. So first you add and subtract. Then you multiply and divide before you get to any exponents. Now we divide. Now we're ready for exponents. So here's my exponent 2. How do you undo an exponent? You take a root. How do you undo a square? You take a square root. To undo a cube, you take a cube root. But when you're doing squares or 4th or 6th degree, even degree exponents, you need to put a plus or minus sign in front of your square root. Here the square and the square root cancel, so we have x plus 4 equals plus or minus the square root of 3. All right, now we subtract 4. So we have plus or minus square root of 3 minus 4. Now, the square root of 3 and the 4 cannot go together because they're not like terms. You can't say that's equal to the square root of -1. We have 2 values here. One of them is positive square root of 3 minus 4, and the other one is negative square root of 3 minus 4. Those represent 2 different x values. We want to write these as points because these are x-intercepts. For an x-intercept, you have your x value and then you have 0 for your y. So here we're going to list x value, root 3 minus 4, comma 0 for my y. And the other one, negative root 3 minus 4, comma 0 for my y. You get 2 x-intercepts. And 23, we could probably squeeze down here. Doesn't take too much space. R of x equals x minus 3 divided by x squared minus 4. If you want to find zeros of a rational function, finding zeros and x-intercepts is the same process. You set the equation equal to 0 and you solve. Now the question is for rational, do I want the bottom to be 0 or the top to be 0? If the bottom is 0, you find vertical asymptotes. That is not what we want. If we want the whole thing to be equal to 0, then I want the top to be 0. 0 over 1 is equal to 0. So I want that to happen. I want the top to be 0, not the bottom. If you have 1 over 0, it is not equal to 0. You get undefined. So if you want it to be 0, you need something like that. So what we're really setting equal to 0 is the numerator, the top. And that's pretty simple. Add the 3 and you get x equals 3. Now, we reread the problem and it says, determine the zeros. That means our answer should look like x equals, not a point. The x-intercepts are points, zeros are x values. Now we can check our answer. If you plug 3 back into your function, you should get 0 as your answer. So plug it back in, I get 3 minus 3 over 3 squared minus 4. I don't want 0 over 0. If it gives me 0 over 0, it's wrong. 0 divided by 9 minus 4, that's not 0 over 0, so I should be good. That's equal to 0. Perfect. So that's the correct answer. And we only found one answer because x minus 3 was only ever 0 at 3. No other x values. Okay, 24. We'll go for maybe another half hour. The graph shown below represents a transformation of the parent function 1 over x. 1 over x, if you don't remember, has these asymptotes at x equals 0 and y equals 0, and crosses at these points and looks like this. So the question is, starting with this red graph, how do we get to our black graph? Well, this bottom piece goes down 2 over 2, and this top piece goes, this one here goes down 2 over 2. So we want to go down 2 and left 2 to go from our red graph down left to our black graph. The same thing happened with the asymptotes. This asymptote moved left 2, this asymptote moved down 2. Okay. How does that show up in my function? My function will become g of x. Write the equation of the transform function. Here's my equation. G of x equals 1 over, if it moves to the right, I write minus. If it moves to the left, I write plus. Since we're moving left, I'm going to write plus 2. Left, right is always next to the x. Up, down is always on the outside. Minus 2 for down. If it were stretched or reflected, you'd put that as a times a number out front. I wouldn't really pay attention to whether this is an x minus h or an x plus h. I think on your last test for chapter 7, it showed it up as an x plus an h. Don't worry if it's a plus h or minus h. Just know plus means left, minus means right. That's most important. So that's our answer for this one. That's the equation of the transformed function. Let's find the range of this next one, 25. Find the range of f of x equals 4 to the x minus 3. It's helpful to know, in order to find ranges, you need to know what the graphs look like. So I would do a sketch if a problem ever asks you to find the range. 4 to the x crosses at 1, and then the next point would be 1 comma 4. And it grows exponentially like that. 1, 2, 3, 4. Minus 3 at the end shifts down 3. That's what transformation happens there. This problem is asking us to find the range. So I start by having this asymptote. The whole thing shifts down 3, including the asymptote, and it becomes this. What is the range of this red graph after that transformation? Well, the range would be starting at -3. Do I have a point at -3? I don't, so I actually don't want to bracket. I have an asymptote there, so parenthesis -3 all the way up to infinity. And that's the range. Number 26, a graph. Let's look at it. Determine any min or max global or local function values of the function graph below. Now, for mins and maxes, they could ask you for a point or a value. A value is not a point. It's either x or y. A function value is a y value. So they want your answer in terms of y values. Y equals. We've got 4 options. We've got global min and global max. We've got local min and local max. So let's write those down. Global is the same as absolute. Global min, global max, and then local min and local max. Global is the absolute highest point or lowest point on your graph. This graph does have an absolute highest point. It's right there. And we want function values as our answers, so y equals. So we do have a global max right here, the highest point, and it's y equals, the y value is 4. Do we have an absolute lowest point on our graph? We don't, because the arrow says go down forever. So you would say none for global min. Local mins and maxes are only these peaks in the middle. This endpoint cannot be a local min or max, not a local max. I won't tell you why right now, just remember that. It's an important fact. So this is your local min, this is your local max. And again, we want function values or y values as our answers. The local min would be y equals -3, and the local max would be y equals 1. Okay. Let's factor number 29 next. Write the function in factored form. This is practice using the AC method. Not quite a formula, but definitely a method you need to know. You multiply, this is A, B, and C, your coefficients. You multiply A times C, and you get 5 times -6 is -30. Our goal is, this is very similar to the way we factor when the leading coefficient is a 1. We want to find 2 numbers that multiply to give you the C here and add to give you this coefficient B in the middle. But when you have a leading coefficient other than 1, like in this case, then you want to find 2 numbers that multiply to give you that product. The way I write it is M times N, 2 numbers that multiply to give you A times C, and add M plus N to give you the middle coefficient B, which is 1. So I need to find 2 numbers that multiply to give me -30 and add to give me 1. Numbers that multiply to give me 30, 5 and 6, 15 and 2, 3 and 10. 5 and 6 are 1 apart from each other, and since I want them to add to be 1, that's my best guess. Add to be +1, so -5 and +6. Those add to be 1 and multiply to be -30. So what do you do next? Once you find those 2 magic numbers, you split your middle term into a -5x and a 6x, and you add them. So we get 5x squared, -5x plus 6x minus 6. This is the easier way to write it. We could have switched it, 6x minus 5x, but you have to be careful. This next part is factoring by grouping. When you have a minus here in the middle, it has to go inside your parentheses. And if it goes inside parentheses, then you would just add another plus here. So if this 6x is a negative, it has to be inside the parentheses. Now we want to factor each of these groupings. I can factor out a 5 and an x from the first one, and I get x minus 1. Plus, I can factor a 6 out of the second grouping, x minus 1. X minus 1 in common, that can be factored out, and I'm left with the 5x plus the 6. And that's factored form. Now, I know in this was chapter, when did we factor? I think it was at the end of the exponent, chapter 5, chapter on exponential functions. So it would have been your third exam, your third test. But there was a problem there where once you factored it, this factor could be factored more. So when you're factoring, always remember to ask yourself, can I factor it anymore? Is it completely factored? The directions here say completely factored form. On the test, it said factored form. It didn't say completely. It maybe would have been clear to say completely, but we always want completely factored. 5 cannot be factored out, so it's completely factored. If this were a 6x plus 6 or 12x plus 6, you'd need to factor the 6 out. Another way to figure that out is when you start, before you start factoring by grouping or AC method, ask yourself, is there a common factor that can be factored out before I use the method I want? And if so, pull that out at the beginning and then factor what's left. Okay. 30 is another factoring problem. and it's a cubic. If you have a cubic, it's either going to be sum or difference of cubes formula, which is not on this review, so I wouldn't worry about that formula, or this method, which is factoring by grouping. It's the same thing we just did, except now we have a negative here. Group the first two and group the second two. Now, this parenthesis has to include your negative sign, like I said, but now that looks like I'm supposed to be multiplying. I'm not multiplying, I'm adding, so stick in a plus sign. What can I factor out of 2x cubed and 6x squared? My greatest common factor would be a 2 and an x squared. And I'm left with an x plus a 3. Multiply it back through to make sure it matches. 2x cubed plus 6x squared. Good. Here I can factor out a negative sign. I always factor the negative out. And an 8 that's in common. So I'm left with x plus 3. These two should always match. If you start with a cubic that you need to use this method on, if they don't match, chances are you made a mistake. All right. Oh, we forgot to do what I said to do in the previous problem. Remember I said check at the beginning to see if there's a common factor? 2, 6, 8, and 24? There is. We could have factored a 2 out. Let's just write that up here to see what it would look like. 2 times x cubed plus 3x squared minus 4x minus 12. And then you would factor by grouping with this one. And you have a 2 out front. What's going to end up happening here is we're going to get this second factor that has a common factor. And if we stop, we'll be wrong because we need to completely factor it. Factor out the x plus 3, and we're left with 2x squared minus 8. So to keep yourself from making that error, always ask yourself, is this completely factored? No. I can factor 2 out. Now, is it completely factored? No, it's not. X squared minus 4 is the difference of squares. And that's equal to, since this is an x squared minus a 2 squared, 4 is just 2 squared, we'd put 2 here and here with a plus and a minus sign. That's the difference of squares formula. This is completely factored because they're all linear and they don't have any leading coefficients other than 1, so there's nothing else you can do to factor it. That would be the problem. Write f of x in completely factored form. There. All right. I'm getting tired, guys. I don't know about you. We only made it through half. I might not be doing all the problems you wanted to see, and I'm sorry, but we'll just keep going and do some of them. 31. This is solving a logarithmic equation. Solve for x. With logarithmic equations, you always want to group your logs on each side by combining logs using properties of logs. That would be the product and the quotient rules and the exponent property. I don't have any logs on my right, so I don't need to worry about that. Both of the logs are positive, so when I combine them into one single log, all I do is I take what follows the log, x plus 4 and x minus 1, and I multiply them if they're both positive. One log. Don't write 2 logs, just one log. Those factors are being multiplied and both plugged into the log. That sum is equal to this product, or this log of this product. Now, by writing it as a single log, we can now change the form using this circle method. To change between log and exponential form, you always start with the base. So 6 raised to the other side 1 is equal to x plus 4 times x minus 1, whatever's in that position. There is another way to do this. You take the base 6 and you say, I'm going to raise 6 to the left side and I'm going to raise 6 to the right side. And properties of logs say these cancel each other out. That's an inverse property, and you're left with the x plus 4 times x minus 1 and 6 to the 1. You get exactly the same thing. I think it's easier to remember just to do change form, but you can do either. All right, to solve this is a polynomial equation. It has to equal 0 and be in factored form. That's how we solve polynomial equations. This is not equal to 0, so I need to subtract the 6 over. 0 equals that. Now, is that in factored form? It's not. Factored form does not allow for plus or minus numbers at the end. So I have to multiply everything out, combine like terms, and then refactor. And again, we are foiling here. So we get a negative x and a positive 4x, and that adds to be a positive 3x, and then a negative 4 minus 6. I can combine the 4 and the 6 into a negative 10. Now it's multiplied out. Now I'm ready to factor. Two numbers that multiply to give me negative 10 and add to be 3. I think it would be a 2 and a 5 multiplied to give me 10. Positive 3 is the sum, so I'd want a positive 5 and a negative 2. Add to be 3, multiply to be negative 10. Solve this. I get x equals, set each of them equal to 0, these factors, and you get positive 2 and negative 5. Are they both solutions? They don't have to be. We have to check for extraneous solutions. How does that work? We're not checking to see that they're correct. We're just making sure they're in the domain, that they're not extraneous. So I write each of the logs down. It doesn't matter what they're equal to, so we don't have to add. And I'm going to plug in each of my x values. Make a little chart here. Plug 2 into this first one, and I get log base 6 of 2 plus 4. That's a log base 6 of 6. That's not breaking any rules. What breaks rules? You need the log of a positive number. Bad would be log of a negative number. We don't want logs of negatives. Now that doesn't mean you can't plug in a negative. It means when you evaluate what's in parentheses, it can't end up being negative. It needs to be positive. So when we plug in the 2 to the first one, we get 2 plus 4 is 6. That is good. That's positive. Doesn't mean the whole log is positive. It means what's being plugged, the 2 plus 4 is positive. Log base 6 of 2 minus 1 is 1. That's positive. 1 is positive, so that is good. That means this is a solution, x equals 2. Or possible solution, if we did it right. Log base 6 of x plus 4 for negative 5. Negative 5 plus 4 is a negative 1. That's bad. That's not what we want. We don't want log of a negative. So this is not a solution. If you write 2 and negative 5 as your answer, then you get it wrong. It has to be just the 2. So we cross that negative 5 out. And the answer is x equals 2. If you were to plug it in and check your original work, it should come out equal. Okay, next. The next few are lines again. Maybe we'll skip these. Let's just talk about, I think we're going to do 38 because that's a trickier one. But let's talk about how to do these. We practiced finding a line that was perpendicular by taking the negative reciprocal. The only thing different here is this, in 37, it's a parallel, oops, you can't see that. It's a parallel line, meaning you look at the slope, negative 3/4, and you keep that slope. So the slope that you want for your new line is also negative 3/4, and it passes through the point, negative 4, negative 4. Before the example we did, they gave us the y-intercept 0, 3, I think it was. And so we knew what b was. This is not b. This is just a point. So the way to set this one up is you use y equals mx plus b, and you plug the point in for x and y. Negative 4 for y, m is negative 3/4, negative 4 for x, and then you solve that equation for b. Once you find b, you know m and b, and you have your function f of x equals mx plus b. For 35, this one's different because they give you 2 points. You don't have the slope and you don't have the y-intercept. You can use change of y. Delta means change. This is a Greek letter or a scientific symbol. It means change of y over change in x. Or y2 minus y1 over x2 minus x1. Use that to find slope. And then you have the same problem we just did down here. You'll have slope and 2 points. Just pick one of the 2 points and plug them in for x and y. And then you can find b. So we're going to skip 35 and 37. We are going to do 38 though, because this problem involves horizontal and vertical lines. And those are sticky when you're talking about functions. Let's just look. If we have a vertical line, is this a function? No. It doesn't pass the vertical line test. Not a function. So if you happen to get an answer that's vertical, you say it's not, the function does not exist because it's not a function. A horizontal line, on the other hand, is a function. It passes the vertical line test. Is a function. So those are okay. But we don't like vertical lines. Okay, so for this problem it says construct a linear function, so find the equation of a line, but it's a function, so you have to say f of x. And there's two parts. A, you want one that's parallel, and B, you want one that's perpendicular. So we have to do two problems here. And the graph that's given is g of x equals 2. What does g of x equals 2 look like? That's the same thing as y equals 2. That means it crosses the y-axis at 2. This is g. Okay, so we want to find a line that's parallel to g for part A and crosses through a specific point. This is given in the problem. So it's parallel to this g of x and it goes through the point 5, 3/5. 5, 3/5 would be 1, 2, 3, 4, 5, and then 3/5 right there. 5, 3/5. What would be a line parallel to G that crosses through this point? It would be this line right here. That's parallel. And what would be a line perpendicular to G that crosses through this point? It would be this line right here. So this is the answer to A, this is the answer to B. Now, the problem is, find the equation of the function, the linear function. Which one has an answer? They don't both have answers. A, the parallel line is a function, so I say the parallel line would be f of x or g of x, I'll say g of x, is equal to, the y value of this line is 3/5. So g of x equals 3/5. That's the linear function that's parallel. Oh, I don't want to say g because this is g. Sorry, let's call it f. F of x, this is the parallel line to g of x that crosses through the point 5, 3/5. Now, the perpendicular line, this up and down one, is vertical. It is not a function. So if the problem says, find a linear function perpendicular to g that crosses through this point, you'd say it doesn't exist. Because it would have to be this one, but that's not a function. So it doesn't exist. Does not exist. Okay, that's 38. Determine the function obtained from transforming log base 11 of x by shifting this parent function 2 units left, stretching it by 4, and then up 3. So we start with the parent function, log base 11 of x, and then we want to shift to left, or left 2, whichever order you write that. Oh, you can't see what I'm writing, I'm sorry. There we go. There's the parent function. Let's write it over here. I want to go left 2, this is 40, and then I want to vertical stretch by 4, and then I want to shift up 3. 3 transformations. Remember, left, right is next to the x, up, down is at the end, and vertical stretching is you multiply by number out front. So we start with log base 11, that doesn't change. X left 2, opposite sign, plus 2. Vertical stretch by 4 means you multiply by 4. If it's a compression, it would say a vertical compression by to 1/2 or 1/3 the height, in which case you multiply by 1/2 or 1/3. So compress is always a number less than 1, stretch is always a number bigger than 1. And then up 3 would be plus 3 on the outside. And then we would call this f of x or g of x. I just picked the letter they haven't given. So if the original function was f, then we would call this g. That represents shift your parent function left 2, vertical stretch by 4, shift up 3. Then there's another one with an exponential function. Same idea, except x is in a different spot. And it wants you to graph it. I think we're going to skip that one. You have to know how to graph an exponential function, but we already practiced graphing one. When did we graph? This one right here. We graphed 4 to the x. And we did transformations on it, 4 to the x in this one to find the range. So we're going to skip this next one, 42. 45, graph, it's a parabola, x² + 2 on the restricted domain. That means you're only looking at half of the parabola. starting at 0 and all the way to the right. On a rectangular coordinate system, then graph its inverse. So what does x squared plus 2 look like? F equals x squared plus 2. This is just the basic parabola shifted up 2. X squared shift up 2. So we have g looks like this. Starts like this, but you shift it up 2. So the vertex moves up to here. And you have a point up 1 over 1. Normally you have 1, 1, but it's going to shift up 2. So that goes up and that goes up. You have this graph. That's f. But they only want, the restricted domain is 0 to infinity. So we actually don't want this left side. We just want the right side. If that's our starting function, how do we graph the inverse? Well, you take the points on your graph, 0, 0. That's not 0, 0. Haha, 0, 2, and 1, 3. And you switch the coordinates. 0, 2 becomes 2, 0. 1, 3 becomes 3, 1. And then you plot your line y equals x. And we try to connect the dots so it looks like a reflection. My units, x's and y's, are a little bit off, so that's why they're looking different. But if you look at the left side and the right side and you tilt your head, you can see that this is like your mirror, your diagonal mirror, and the left and the right look the same. That should happen with inverses. So this would be f inverse over here. All right, we're getting close, guys. Find the inverse, that's a good practice. Not the graph, but the equation of f of x equals 3 times 5 to the x minus 2. And then graph the inverse function. We may or may not graph it, but we'll definitely find the inverse. Always start by writing y equals, and then switch your variables. Okay, I want to get to the y. Before I get to the y, I need to get 5 to the y by itself. So again, we're going to do PEMDAS backwards to get the 5 to the y by itself. First, we add and subtract. Let's get rid of the 2. Then we'll get rid of that 3. So now we have 3 times 5 to the y. Divide both sides by 3. So I have 5 to the y equals x plus 2 over 3. All right. Here we go. I got the exponential part by itself. If it's an exponential equation, which this one is, or a logarithmic equation, usually it involves the opposite, the inverse. So since it's exponential, I'll need a log to solve this. So I'm going to do the base raised to the opposite side, or not raised to. Since this is exponential, I want to change it to logarithmic form. So my base 5 is going to be the base of my log, and I write log base 5 of this equals the y. And that solved for y, which is what I wanted to do. Since I started with an f, I'll write my answer as f inverse of x equals this equation, log base 5 of x plus 2 over 3. Honestly, they're asking you to graph this. I don't think they should have asked you to graph this, because we didn't graph horizontal stretches and compressions, which is what this 1/3 would be. That would be a horizontal stretch, but we haven't done that in this class. So they're not going to give that to you on the final. It would be something like just an x plus a 2, not x plus 2 over 3. But, you know, we're not going to graph that because that involves transformations, but let's just make sure we remember what a logarithmic function looks like. It's graph. Let's graph log base 2 of x, just as a quick review. This function crosses the x-axis at 1, has a horizontal vertical asymptote, and it goes like this. Its second point, whatever the base is, it's 2, so you go over 2, up 1. And that is the same point that you get from plugging a 1 into 2 to the x. So if you're doing a table of values and you plug a 1 in, 2 to the 1 is equal to 2. So that point, 1 comma 2, when you go to the logarithm, because they're inverses of each other, becomes 2 comma 1. That's where that point comes from. Anyway, that's what the starting logarithmic graph looks like. You should know what logarithmic functions and exponential functions look like, the parent functions, for sure, because you might get something like that on the final. All right, let's go back. I ran out of paper. A few more problems. We have like 5 more minutes. What problem was that? That was 46. Let's do 50. Determine the solutions, real or complex, to this equation. Now, solve an equation. Solutions to an equation. What does that look like? To solve an equation, your answer should look like x equals numbers. So that's the form that we want to give our answer. I need it to be equal to 0. So let's push this x squared over here to make it a positive 2x squared, rather than subtracting the 3x squared over to the left, which would give me a negative 2x squared. I don't want a negative x squared. Oh, I actually need to push the 5x over too. I could have done that at the same time. So I have, in descending order, 2x squared plus 5x plus 7. To factor this is the AC method. Again, we already did that. So I'm not going to go through the whole process. I'll just show you the answer for lack of time. Oh, but guess what? The AC method doesn't work. So if you try the AC method and you can't find two numbers that multiply to give you 14 and add to give you 5, this method does not work. So now we use the quadratic formula, which is, you should have, here's another formula you should have memorized. We're going to box it. X equals, when it's equal to 0 and you're solving a quadratic equation, negative b plus or minus the square root of b squared minus 4ac all over 2a. I think I put the song of the quadratic formula on one of your videos. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Make sure you know that. You don't have to sing it though. I won't grade you on that. Here is A, 2. Here is B, 5. And here is C, 7. So we're going to plug those in. Negative 5 plus or minus the square root of 5 squared minus 4 times 2 times 7. If 5 were negative, I'd need to be sure to put it in parentheses, so I'll put it in parentheses here. If you square a negative, it becomes positive. All over 2, and this is not a negative b, this is a negative 5. Negative b. B squared minus 4ac all over 2a is 2. Now we simplify. Negative 5 plus or minus the square root. This is 25 minus 8 times 7, minus 56. 25 minus 56 is a negative 31. All over 4. Now, negative under the square root means this is complex, but the problem did say determine the solutions, real or complex. The only thing you'd want to simplify here, since 31 is not a perfect square, there's no square number factors, you want to pull the negative out and it becomes an I. So this would be plus or minus I root 31 all over 4. Don't try to simplify if you're going to make mistakes. If you're not really good at simplifying, just leave as is and that's fine. It did not ask for x-intercept. It asked for solutions to the equation. So my answer would be x is equal to, you could write with a plus or minus sign, or you could write them separately. Negative 5 plus I root 31 over 4. And that negative sign is only part of the 5. It's not out front of the fraction. So be careful the way you write it. Comma, negative 5 minus I root 31 all over 4. Those are your solutions. That's a formula. That's why it's boxed in red. Alrighty. I've got like the rest of the problems on the review almost circled. What else do you need to know? Because we're just about out of time. Solve an exponential equation. More transformations, which we won't do. This is an intersection point that is then shifted. What happens to the intersection point? This is an intersection point that is then inverted. What happens to the intersection point? This is find the equation of a line that has the same y-intercept as g. Well, how do you find y-intercepts? We wrote it on the other page. You find y-intercepts by plugging 0 in for x. So if you plug a 0 in here, what do you get as your answer? That would be the y-intercept for your line, or b. So that's how you find b. Average rate of change is your slope. So they've told you slope is 4. You can find b by finding the y-intercept of this function here, and then you can find the equation of the function. Here, these two problems, you're supposed to find the equation of the parabolas. Here, you're supposed to find the inverse of a quadratic, which involves a square root, but square roots you get plus or minuses when you're solving. Since this is x, you know, I didn't do this problem for you. I don't know how good the video was that I included in that section, so I'm going to do 57. If f of x is equal to 3 times x plus 2 quantity squared minus 17, this is a parabola stretched by a factor of 3, shifted left 2, down 17. So the vertex is at negative 2, comma, negative 17, but it's a restricted domain. Why do we restrict domains when we talk about inverse functions? Because we need it to be one-to-one, and parabolas are not one-to-one. They do not pass the horizontal line test. But by restricting the domain, what we do is we cut it in half. That means negative 2 must be where the vertex is. So that's going to be negative 2 comma something. We cut off half of it. We either take the left half or the right half. And then it's one-to-one and we can find its inverse. So if x is bigger, it means we're taking the right half. This is the right side. If x is less than your number, then you're taking the left side. When you're taking the right side, you're going to end up with the right side gives you as an inverse the positive square root, and the left side gives you as an inverse the negative square root. So let's do that here. To find an inverse, you write y equals, and then switch your variables. Y. There we go. Solving for y, I want to do PEMDAS backwards. I want to get the y plus 2 by itself. Add the 17. Similar to what we did before. Divide by 3. Now I have y plus 2 quantity squared by itself. Next, I get rid of the exponent. PEMDAS backwards. First we added, subtracted, then we multiplied, divided. Now we get rid of the exponent by square rooting both sides. But when you square root both sides, we did this before. Maybe it was finding x-intercepts or zeros of a quadratic. You put plus or minus in front. So we get y plus 2 equals plus or minus the square root of x plus 17 over 3. Guys, I am kind of particular about the way you write square roots. The whole thing is being square rooted. If the 3 is on the bottom like that, it's wrong. The whole thing is under this square root sign because you divided by 3 before you took the square root. So we were taking the square root of the whole thing. Put parentheses around it so it's nice and clear. Inside the square root sign. Okay, then we need to subtract 2 off. So we get y equals plus or minus the square root of x plus 17 over 3 minus 2. But we need to pick one of those because this needs to be a function. Functions cannot have plus or minus signs. So remember I said up here, if you have the right half of your parabola, then you pick the positive square root. If you have the left half, you pick the negative square root. Since I was given the right half, I want to pick the positive square root here. So I cross off that negative sign. So my answer is f inverse of x equals this equation with a plus sign. And you can put the minus 2 at the end or the beginning, it doesn't matter. Square root of x plus 17 over 3 minus 2. That's that inverse function. Parabolas always get square root inverse functions. Okay, almost done. This one here, which relations are functions? We already practiced with ordered pairs. You just make sure there's no repeated x's, and if there are, like this one here, you need to make sure their y's are repeated or not. If the y's are the same, it is a function. If they're different, it's not. So this one is not a function because it repeats the x coordinate of 2 with different y's. That means you get points on top of each other. It does not pass the vertical line test. Here, it does not pass the vertical line test, so no. How do you know if an equation is a function? Well, you want to look for plus or minus signs are bad. There's no plus or minus sign. And y squares are bad. That's basically what you're looking for. I don't have a y squared, I have an x squared. That's okay. I don't have a plus or minus sign in this equation, so this is a function. And then last but not least, let's practice synthetic division once and then we'll be done. Okay. It's that long video. I'm not sure what to do with it, so you guys can watch it. I don't know if I can upload an hour and a half video onto YouTube. We'll see. Maybe I'll have to split it. 3x cubed plus 4x minus 10 divided by x plus 2. I should have stopped the video and started it again so it wouldn't be too big. All right. If you're dividing by a line or a linear polynomial, then you can use synthetic. But you have to also pay attention for your polynomial if you skip a power of x, which we have. So go ahead and rewrite it before we start our division with the 0x squared written in there. And then we won't make mistakes forgetting that 0. For synthetic division, you write these coefficients. And then the number out front will be the opposite sign of what you have here, -2. Carry your first number down. Then multiply, and we get -6, right? The number here, then we add. So we always add going down, multiply going across here. 12, add. Multiply, -32, add, -42. That's your remainder. This is your polynomial. The first term on the right of your polynomial is your constant term. This next one is your x term. This next is your x squared, and you just keep going up. However many terms you have, that's the power of x. So our answer is this polynomial plus the remainder over the original divisor. A polynomial, this is called the division algorithm, divided by a divisor is equal to a quotient plus a remainder over your divisor. The problem says divide. That means you want your answer in this form, if it just says divide. So we write 3x squared minus 6x plus 16 plus your remainder over your x plus 2 divisor. We also could have done that with long division, but I'm not going to because this is too long. We're going to be done. Anyway, I hope that was helpful for you. Good luck studying. I will give you some more instruction on what you have to write down as written scratch work and upload for your final exam. I haven't finished deciding, but I will let you know soon. Happy studies.